So in this part, we talk about the movement, the motion of waves. Now, as we said before, waves, as they move, they carry energy. Examples of waves: sound. Sound travels in a medium from a source that producing the sound to our ears. And sound is carrying energy as it moves. Another example is light. Light is also carrying energy. It comes to our eyes in different forms of waves, what we call electromagnetic waves. Signals that reach our radio or television sets, also they are part of the electromagnetic waves, and they carry energy as they travel. We know, of course, that sound always needs medium to travel in. Medium, for example, air. So sound can travel in air, but it can never travel in empty space. This is different from electromagnetic waves, which can travel in vacuum, that's in empty space. Now again, I want to stress that wave is not matter. So when the wave is spreading, moving in space, matter is not moving with the wave. Just look at this picture to understand this important idea. As you shake a string with your hand up and down, you are generating a wave, and this wave is spreading along the string. Now, the pieces of the string themselves, the matter, the pieces of the string are vibrating up and down. They just go up and down in a continuous vibrational mode. But the wave itself is propagating along the string without the movement of the pieces of the string itself. Another example, if you drop a stone in a pond, you will produce waves, and these waves, in the shape of circles, the growing circles, they spread on the surface of the water. The pieces of the water itself, H2O, the molecules, the pieces of water, simply they are vibrating up and down on the surface, but they are not moving with the wave itself. I hope you understand this important idea. Well, I mean, this slide repeating the same thing. I don't want to read it again. Please, you read it again and try to understand the important point we are talking about. Now, because waves move, spread, this means they have speed. Of course, the speed of a wave, for example, in the case of sound, it depends on the medium it's traveling through. But whatever the medium is, the speed of a wave, its wavelength, and its frequency are all related. Let's take a very simple example. Let's look at this water wave. And if you look at the picture, you can see that the wavelength is 1 meter. 1 meter because look at the distance from one crest to the next crest is 1 meter. And that's the wavelength. Now this wave is not at rest, it's spreading, it's moving. So this bird, as you can see, the bird, he's seeing waves coming to its location. Now these waves are spreading, are moving. Now if you read here, it says that the wavelength is 1 meter. Okay, we agree. And 1 wavelength per second passes the pole. So this means every second there's 1 complete wave moving. So what's the speed of this wave? Well, because 1 full wavelength is moving in 1 second, the distance is 1 meter and the time is 1 second. So this gives you that the speed of the wave is 1 meter per second. Now we can think about it and try to find a formula to calculate the wave speed. Let's read what is written here. It says that if the wavelength of a wave is 3 meters and if 2 crests pass a point each second, so what is the speed of this wave? Well, here in this example, we have 2 complete waves are passing a point each second. Now, one wave is 3 meters of length, two waves are 6 meters. So the distance is 6 meters. In 1 second, they are moving, passing a point each second. So this means the speed is 6 meters per second. Now the formula really is very simple to use to calculate the speed of a wave. A speed of a wave, which we'll call v, is equal to the wavelength, which is denoted by this symbol, lambda, multiplied by f, the frequency. So if you multiply the wavelength times frequency, then you will get the speed of a wave. And that's not difficult to understand if you go back to this example and to think about it, how these three quantities are related. Now, if we talk specifically about sound, now we said that sound needs medium, for example, air. Now we know that the speed of sound in air is always the same. So the product of wavelength and the frequency is the same for every frequency of sound. And the equation to use is this one again. The speed of sound, of the wave of sound, is equal to its wavelength times its frequency. So you can see now, if I have, let's say, a small lambda, small wavelength, then its frequency should be high in the sense that if you multiply those two numbers, you should get always the same quantity. Let's go to the next slide and to explain this more carefully. I have a table here, and in the first column, it shows different wavelengths of a sound wave. In the second column, there's the frequency in hertz, and then the last column contains the speed. Now, if you look at the last column, the speed, you can see that you get always the same number. This is the famous speed of sound in air, 340 meters per second. Of course, this is really need to be clarified. It depends on the temperature of air, it depends on the air pressure and so on. So this is commonly known as, this is the speed of sound for cold air at 0 degrees Celsius and at the sea level. So the air pressure is what is at the sea level. If you change the temperature, if you change the air pressure, this number will slightly change. But let's not dwell on this issue. So if I took this number, for example, a wavelength of 2.13 meters, its frequency is 160 hertz. Now, if you multiply the wavelength by frequency, you will get 340 meters per second. That's the speed. Now, if you change the wavelength, for example, if you look at this table, the wavelength is going down, it's becoming smaller. Now, if you look at the frequency becoming bigger. But you can see that in every case, if you multiply the wavelength times the frequency, you will get the same wave speed. So if the wavelength goes down, becomes smaller, the frequency becomes bigger, and vice versa. Let's take a very simple problem. If a water wave vibrates up and down 2 times each second, and the distance between 2 wave crests is 1.5 meter, so now the question is, what is the frequency of the wave, what is the wavelength lambda, and what is the speed? Now, of course, this is not a difficult question if you think about it. In fact, let's go back and read it again. Let's read the first sentence, the first line. If a water wave vibrates up and down 2 times each second. So what do you conclude from this sentence? So the vibration is making, you have 2 vibrations each second. So that's the frequency. The frequency of the vibration will be the same as the frequency of the wave. So frequency should be 2. The wavelength is simply 1.5 meter. It's already saying that the distance between 2 wave crests, two close wave crests, is 1.5 meter. Since we know the frequency and we know the wavelength, we can simply calculate the speed by using the formula. The speed of a wave is equal to wavelength times frequency. You multiply 1.5 times 2 hertz, and then you will get 3 meters per second. Another question. What is the wavelength of a 340 hertz sorry, 340 hertz sound wave when the speed of sound in air is 340 meter per second. So let's think about it. Now the frequency is given is 340 hertz and the speed is also given 340 meter per second. So what do you think will be the wavelength? The wavelength should be 1 meter. Why? Because if lambda, the wavelength is 1 meter and the frequency is 340, if you multiply them, you should get the speed. So 1 times 340 hertz should equal to 340 meter per second. This is the end of our part. So let's finish with a few questions. The first question is, we mentioned that sound travels in air. But the question is, does it travel in water? Does it travel in liquids? If yes, what do you think? What is the speed of sound? What about solids? Does sound travel in solids? Now, to answer those two questions, please do some research and let's talk about this in a class. I'm expecting you to have some input on this issue.